generous support of the School of Humanities and Sciences at Stanford University. Snap, Crackle, Pop, the value of the laboratory experience in the sciences. A talk by Richard Zare. As part of the award-winning Teachers on Teaching series sponsored by the Center for Teaching and Learning at Stanford University, Richard Zare, the Marguerite Blake Wilbur Professor in Natural Science at Stanford University and Chair of the National Science Board, discusses the importance of the laboratory when teaching science.
Indeed, let me start, if I might, with a quote from my thesis advisor. This is Dudley Hirsch, something he wrote. I hope we can read this. Let me focus this, okay? And he writes, I'm going to read it to you if you can't. He writes, "Too often, laboratory work in typical general chemistry courses has a ritualistic character. Students follow a carefully specified protocol enshrined in a laboratory manual and interpreted or reinforced by pronouncements from priest-like figures garbed in white coats. The teaching follows. This fosters slavish imitation and timidity rather than the self-reliant, innovative, experimental spirit that is the essence of science." Hirschbach's a very special character. Hirschbach is one of the 2 undergraduates at Stanford University who have ever won the Nobel Prize. Okay, he won the Nobel Prize in chemistry. The other one from Stanford University undergrad is a freshman dropout by the name of John Steinbeck. Okay. Now, really, I'm afraid there's a lot of truth to his quote. And you need to think hard about this matter. There's an increasing tendency to try to do away with labs for various reasons that we'll return to. And indeed, I have one colleague who's been serving on President Casper's team to worry about innovation using computers, who says that we should replace a lot of our labs with a computer experience. And it's important that we capture what the future might be. So I brought that along in hopes that you can all see it as to where we're going. Now, the claim is made that medical doctors can do better now, not doing gross anatomy, but actually putting their hands into some type of gloves and wearing goggles and using a computer to carve things up and learn about gross anatomy. Maybe it's true. Maybe we're not there yet. I know at the moment that if I see a doctor for surgery, that's not the doctor I want to see, who's been trained only that way for sure. Computers are wonderful, and indeed they have a wonderful place in the lab, but I think nothing replaces the real experience. And the real experience, I must tell you, is at best a comedy of errors. Okay? Progress in experimental science consists of going from one failure to another with undiminished enthusiasm. Those of us who've been there know this. And too often our labs, because of not having the time, etc., they're all arranged to perfectly work and show something, when in life, it isn't that way. In fact, you learn so much from what doesn't work in different ways. Let me turn now to some lab demonstrations to talk about some of these. I had here, I thought, a wonderful cartoon about this. I might share this with you. I don't know if you can see this. You see the, let me try. You see the instructor, lab bench, all the students, instructor preparing the demonstration, and well, is it as bad as that? There's one very dramatic such example which I wanted to illustrate with you, and then there's some others which are of a more subtle nature. Let me start by turning this off and actually turning to the matter of the glowing gherkin or pickle, which I think I can set up for you. We have here a transformer, the electrical line with 2 prongs. grateful to Brian Bean to put this together. Let's check the moment that this is off. It is off. That's important. Now we're going to plug this in. Okay. And we need some pickles. Now, not any type of pickles. Cucumbers don't work. In fact, the saltier the better. So really kosher pickles are what you're after. Okay, a little bit of effort here. Let's pick out a pickle. Not so easy. Okay. And now, let's take these electrical leads, and we'll place them one side, one in another. And let's dangle this so that you can see it. Now, before I do that, I want to make sure that we're in good shape. That's before you. It is. We'll collect any pickle juice underneath. Just a moment, like so. And we're now going to pass current through this pickle. And I'd like to dim the lights a little, just in the front if it's possible, so that we can see what happens. So we turn on our switch, and we start to pass current through this. And starting to steam, notice. And if you look, what do you see? You should see a yellow glow, right? It's coming from this pickle. Let me turn this back off, turn this moment, and if you were to feel this, it's now warm. Bring these a little closer. Try one more time. And get this effect for you. Pretty clear. Okay, and indeed, if you go from 110 to 220, you can read by this. What else to tell you about this? Only one side of the electrode is yellow, not the other. You need to think about that. Why is that so? And then what can you learn from this? Why does it matter? Okay, so it's a lovely demonstration that I learned from a fellow by the name of Appling, Jeff Appling, who's now at Clemson, about this pickle. How does this fit in? Turns out what we know about the stars, for example, is only what we see. We see at various radiations, and one of them is the visible, and we analyze them into colors. And then we make wonderful statements about what goes on, assuming that whatever takes place on Earth is transferable to far out there where we haven't been and are not likely to go in my lifetime anyways. What would we conclude about a pickle far away? We would conclude that it was raging sodium inferno, right? When really it has about 16% sodium, but not that at all. You're missing a lot. It's the same way of looking at a flame and not understanding from the flame of a candle all the processes that are going on. The flame of the candle is normally yellow, same thing which is coloring our pickle. And you can use this many ways to teach about things. I like these as lecture demonstrations. They're easy to do, and I find that if you do that, well, a lot of lectures are forgotten, but the certain moments, some moments are captured and are brought away, and they really work with a type of lecture demonstration. So that's one form of, if you will, lab experience that's hands-on. And so now I'm going to shut this off, take this down, and I'm sorry there's no great way of disposing of this. And so we now have some burnt pickle flesh to deal with later. Let's continue with light. Another piece of light that you can often use is your overhead projector. And here it is. Here's our overhead projector. And I want to turn this overhead projector into something that will illustrate for us how indeed a spectrometer works. You notice I have here a green laser. This is a green laser beam. And if I send this green laser beam through this piece of grating, you see all the different green spots? Of course, it's transmitted, and then the various orders. If I actually can bring this and tape this, well, I need to find my tape. Okay, there was tape on the overhead table. Aha! Thank you. It's an empty box. Okay. So, I need to hold this like so. And I need to, you see some tape? Ah, I see. Thank you. That'll help. This is just so I can attach it. I'm now putting some tape onto our overhead to try to hold it in place. And now we need to put in some slits. Let's try this. Okay, and I want to again dim the lights, if I might, and explain what we have. Can you see this? So what I have is just a piece of cardboard. It's cut out with slits, 2 of them, and I see the image coming through, which is the undeflected image, 0th order from the grating, and then I see the type of thing that Isaac Newton would have been proud of when he would have used a prism instead of a diffraction grating in his day. Plastic didn't exist. Okay. Needed some chemistry. Okay, but okay, we got this. We see the colors. Let me now bring up some solutions. Here are some vials that contain some organic molecules that are colored. Let me place this one, for example, over one of the slits. What do you see? If you compare this side with this, you see that this color is missing. It's been clipped away, eaten up. It's being absorbed. This looks yellow because it's really absorbing violet. We really can, and then we can talk about what concentrations with this, and we can learn how to characterize this. Here's yet another dye. Let me show you the nature of this one. This one eats away the green. See the red coming through and the blue going through? And for fun, I brought along some safety glasses. The safety glasses, when you work with laser beams, let's look at them. How effective are they? Do they really work? Okay, so let me put one lens in. And what do we see? That's through in the red, but it really cuts out here where it's supposed to. That's the type of thing that we're dealing with. Okay, so you can use this and go on very easily to illustrate all types of properties of light interacting with matter. And I've used this in my lectures, and I think it allows students to get a feeling for this rather than, there's a black box called the spectrophotometer. You put the cell in and it reads something on a meter. That's not the same at all. And brought along some solution. Here's a beaker. I'm going to turn this off. Get you to see something, I hope. Here's some dye solution. I'm going to transfer to here. Let's take my laser pointer, which I have now misplaced. Here it is. And shine this into this. What do you see? This, remember, is green. You see yellow. You can explain why yellow, the fluorescence, etc. Molecules falling back to the ground state, different vibrational levels of the ground state. And you notice how much brighter it is here than it is here? In fact, it has an exponential decay. And that's, you can then use to illustrate what's called Beer's law and bring that back to absorption. And absorption always has, of course, more in the ground state than in the excited state. What happens if you have more in the excited state than in the ground state? Then you get what I call is Beer's laws backwards. Reeves' law, okay? And Reeves' law says instead of having loss along the medium, you have gain. And what's gain? That's the laser. That's indeed how a laser works. Make more in the excited state than the ground state by some non-equilibrium process. Okay, great. Let's put these aside for a moment and return to some comments that people made. I was looking about this, about what matters. People say, oh, what has happened? We've got to remove a grating. Okay, this will help. Okay, that. Okay, let's put this on here so you can read it. And I'll read it to you because I'm not sure how well this works. It says, one ultimate demonstration. How is it possible to walk on burning coals and not get burnt? People do this. I have seen pictures of this. I've not done this personally, but I believe you can. Two explanations are given for why this is so. One's the sizzle effect, or Leidenfrost effect. What this means is that you're so scared, you're sweating. And you normally sweat anyways from your skin, okay? And the sweat against the hot coals makes steam, and that basically insulates you from what's going on. That's one explanation. Another explanation is there's not enough heat. It isn't that it's not hot enough. It's certainly plenty hot. It's something like 600 degrees Celsius. That's, as you know, burning coals, right? Very hot. But there isn't much heat content in wood. It's not easily able to transfer it. And this is a very good explanation, I think. Both are true, and they don't contain all that much heat. It's very much like talking about water, about a squirt gun. It may have lots of pressure, but it has, depending, little volume. In this case, little volume, little heat. And these two explanations are put forward. I've met someone, and some of you might recognize his name. This is Gerald Walker. And I wanted to quote to you from a person by the name of Cecil Adams, who writes something called The Straight Dope and publishes it, syndicated columnist. And he says, I've just spoken to my bud, Gerald Walker, who's in Cleveland, Ohio, where I grew up. And he's the former Scientific American columnist, and it turns out the G. Gordon Liddy of physics. Okay. And it's true. As a classroom demo of the Leidenfrost effect, Gerald not only walked on hot coals. Incidentally, he gave it up after getting badly burned once. He was so cool, his feet didn't get sufficiently damp. He also dips his bare hand in water and then plunges it momentarily into a vat of molten lead, which is 700 degrees Celsius. And says Gerald, who's even done this on the Johnny Carson show. Here's the quote that I thought so arresting. There is no classroom demonstration so riveting as one in which the teacher may die. Is this really necessary? I hope you've seen, from what I've started to show you, this, I believe, that, you know, this is what you expect G. Gordon Liddy to say. But you can do such things, and they do make a very lasting effect. Some of the prettiest I've seen has been done with liquid nitrogen. I happen to bring some here. Right? And we'll put some liquid nitrogen into this door. What is this? Is it steam? No, it's condensed water, right? This is so cold. This is so cold. And indeed, I can put some in a styrofoam cup. Okay. We have a liquid nitrogen tank over by mud and chemistry. Some of you may have seen the steam from it. And you can do all types of marvelous things with it, such as taking a balloon. Okay, and I probably can't do this. I think others are going to be better at this than me. That's not going to hold. Okay. I could just get it around. No. Okay. Well, we won't do it that way. And that's not going to fit. Have to let something out. Okay. And if you dunk this in, right? And of course, this gets quite cold. More dramatic still is a banana. The laboratory technique's impeccable. And we have now a nice cool banana. The properties of cold banana are quite different. This is still boiling away as it cools down. Taking time to let's turn this over. Maybe good enough. Okay, and such a thing. Well, try some more. It's going to show you it shatters pretty readily. I will come back to that in a moment. Here is some liquid nitrogen, as you saw. And I just wanted to illustrate to you the thing. I have a friend, Professor James L. Kinsey from Rice University, and he actually gargles with this stuff before classes. And you can understand how you can do that. I've never brought myself to that point yet. But it is certainly easy to take your hand. This is so cold, and pour it over it, right? And of course, this is harmless. This is nitrogen, though it's technically a suffocant, which means too much of it forces the oxygen out. So, and try again. Right. And you know you can't do that with a room temperature banana at all. Okay. So we have that. And many things to illustrate. Now let's go on with this to talk about the uses, if I might. More stories, if I can share with you about what to do. It makes a huge difference to people to have a hands-on experience, I find. If I went around and I talked to people why they go into various fields of science. And my experience has been not because there was a great homework problem that they solved. They don't remember the homework problem. And the thrill of solving a great homework problem is akin to making a great move in chess, playing a great bridge hand when you understand what to do, etc. It's wonderful and all that, but it is generally not very lasting. I'm sorry to say. The thrill that is lasting is when you can do something with your own hands and think what it means and interpret it. That's what matters. That's why people decide to go on, generally, if they do, into some form of science one way or another. Whether they go into theory or experiment afterwards, hey, that's a detail. I'm talking about what causes this. So you want to do this very early on. One of the things we must do is learn how to bring this into the grade schools, lower down levels. So I'm maybe you can tell, imbued with that enthusiasm. In fact, so much so that I worked with some people to write a book. This is Linda Cicero's picture, so remember that. And this is laser experiments for beginners. These beginners are people in high school or just beginning college. It's possible, not using this laser, but a helium neon laser is very cheap, to write a book full of experiments to illustrate all types of things that you can do, from hole burning in solutions, leaving transparent streaks and things, to all types of other things. I brought with me little Dixie cups that contained sodium bicarbonate and vinegar. I was going to pour the two together and watch them foam as in various baking reactions and such. I passed out to the first graders the sodium bicarbonate and vinegar. Before I could tell them what to do, not one, but several students had eaten them and were foaming and belching. I'm glad I didn't bring copper sulfate, which is a bad poison. Okay, I hadn't encountered that. I brought along some lecture demonstrations of the type, again, you could do. I brought along something called an oscillating chemical reaction, which illustrates so much. So interesting to actually see a reaction which, as it goes on, forms order within itself. Talk about heartbeats and various other things. I had this, it was driven by the heat of the overhead, and you could project it. Class said it didn't compare with television. No interest at all. Couldn't make the context. I brought along thermite. They loved it. I brought along magnesium ribbon. The class, all they wanted to do was burn more magnesium ribbon. It was very discouraging. Okay, so you have to know your audience. That's one thing for sure in this, and I didn't in that case. That was part of my experiences. I've had some other experiences. I've had the opportunity, the rare pleasure, of trying to teach about science to non-science undergraduate majors. First thing, in a course that would be called Chemistry 1, 2, 3, as it's as simple as 1, 2, 3, but people interpreted that as 123 as some high-level course, and it was very hard to get them to take it. So we changed the title later to Chem 1, with no great increase in attendance, I might say, as well. But what was interesting about it was the ability to do labs. And the labs I designed were done in the dormitories. There's a great advantage to that. I truly believe that an educated person, at least from Stanford, ought to know about science and technology and mathematics, what goes on as well. I think it's very important we have that type of requirement. I think you just do yourself in if you don't learn about that. Anyway, stick in the world we live in. So I made up a bunch of experiments that could be done in the dorms without, killing dorm pets or the dorm roommate and so forth. And they were the first experiment. I want to share them with you because I think you'll find them interesting. Perhaps what to do is I asked them, please, after I showed them a wonderful movie about powers of 10, to find if you take salt water and you dilute it serially, what is the point where you can quit tasting salt water as being salty, that it tastes the same as tap water? The other thing I did is I gave them an ammonia solution and asked them, when, if you keep diluting it, could you quit smelling ammonia? And the third one I gave them was a food coloring. Okay? And I asked them, when could you keep diluting this blue food coloring until it no longer can be detected as blue? Turns out your eye is much more sensitive. That had the parts per million type level. The others were parts per thousand. And this allowed us to talk about the terrors of parts per trillion in our environment, what it meant, and why we care, and when we care, and what that meant, what these numbers mean. And it helped us get over what newspapers keep doing, which are these leading and trailing zeros, which I have to count to figure out what they are. Whereas I want them to learn powers of 10 and what they're like and what numbers are like. Because otherwise, how can I ever teach what Avogadro's number is, really? And I did want to, and I did. I think I succeeded in getting a sense of that across to a group of people. Because the class came back, and they complained about this experiment to me. Their complaint was they enjoyed doing it, and they got, incidentally, about 10 times more people were involved in these experiments that were taking the course, because they always, going on in the dorm, involved everybody, right? But they complained. They said, we got different answers. So-and-so could still see it as being blue when so-and-so could not. What's the right answer? That's an important question. And that led to the idea of reference standards and instrumentation. That's a big thought. After all, the history of science started there and had to build up to how you do that. So I thought that was a good first beginning. I gave them some other experiments to do. One of my favorites that I enjoyed was a kinetics experiment. I had them look at Alka-Seltzer tablets. My wife, Susan, helped me with this course, and she would go and buy the Alka-Seltzer tablets from the local store. We needed a number, as you'll see. We raced Alka-Seltzer tablets in hot water versus cold water, how fast they dissolve. Guess what? Hot water's faster, right? You knew that already. And we raced Alka-Seltzer tablets in a glass that had already had an Alka-Seltzer tablet dissolved in it versus one that didn't. They're the same. It's not really much controlled by what's been dissolved there before. That's fine. Then I asked them to make a prediction what would happen if you cut an Alka-Seltzer tablet in half and you raised a half an Alka-Seltzer tablet against a whole Alka-Seltzer tablet? When would they first disappear? They made their prediction. I asked them then to make the observation. Observation was done. They come out about the same. Then I asked them to make an explanation. And indeed, I had them, prior to that, powder up Alka-Seltzer tablets and show how quickly they went. And more than half the class, without being told, decided that surface area was an important matter in controlling the rate at which Alka-Seltzer, the dissolution of Alka-Seltzer tablets, okay? Oh, what a relief it is, dependent on the surface area. So how fast. I'm trying to get you a sense of something here. Of course, my wife had a great time checking out these hundreds of Alka-Seltzer tablets. I remember she going to one of the local stores here, and the person from the checkout counter looking up at her and saying, "It must have been quite a party." Ah, dear. So now I've mentioned some of that and its value. Let me turn to, if I might, a good news and bad news, and then talk about this in some more detail. This is sort of a summary of my thoughts on this, if I can. Okay. What we have is that there's good news and bad news with laboratories. Hands-on experience and investigation are useful for teaching skills. Certainly believe that. The use and handling of equipment makes a difference if you drive a car to have driven one before rather than read about it. Okay. And the strategies of independent research. They allow personal discovery. They teach students to focus on observation. They teach students to deal with uncertainty. And they teach students to distinguish between fact and interpretation. Really key matters in science. When done well, a positive lab experience, one or more of these, are some of the best remembered teaching experiences you can produce. And they can be most decisive in choosing a career in the sciences, all types of sciences. I believe this. So they matter a lot to be able to do something this way. That's the good news, part of it. Now let me tell you about the bad news. Labs have real disadvantages. They are costly. No question. Stuff, particularly what chemicals you use, or whatever supplies you use of any sort. They are time-consuming. Any of us who've been involved in labs know they're very time-consuming. They can completely take all your time, etc. Faculty often view labs as the domain of teaching assistants. This is so. And indeed, in terms of a reward structure, time spent on labs is very seldom given much reward. You should, spend your time doing research, not working on developing a lab, etc. Worse still, laboratory exercises are often cookbook activities. This is going back to this question, Fred, of mirroring science. Fortunately, often they do not. They haven't been designed that way. They keep students very busy, but do not acquaint students with the discipline and the experience of true investigation. This part is a real waste. Students remember this negatively, and I don't see. We got to try to work to not have that happen. It's important then to design a lab and not over-design it. To let there be ways that things can go wrong and do go wrong and take advantage of it. I must share with you that some of the best lecture demonstrations that I have done are those that in some sense are failed, okay, to talk about it. And in fact, I've even moved towards using some of them as a way to start a course. In teaching an honors freshman chemistry course, I started by electrolyzing water with two burettes that collect the gases of hydrogen and oxygen. I could take a burning splint, show one was a pink flame of hydrogen, the other one was burst into a big flame of oxygen, right? That really worked. Then, of course, having burettes, I was able to read. And they all knew the formula of water ahead of time, H2O. And they knew that there were going to be twice as much hydrogen as there was oxygen. And we looked at the burette, and it didn't come out that way, not at the beginning at all. And then we talked about it. The beginning first class, people who've had AP credit in chemistry at that time, Was it that the formula for water that they'd come now to Stanford is no longer H2O? Is that giving them something very strange? What was happening? And we talked about possibilities of what was really happening. What was going on at the electrodes? Was it possible that oxygen and hydrogen had different solubilities in water? Is it possible that fish actually use dissolved oxygen, et cetera, and so on? There's much to learn here. Thank God that's not how the formula H2O was first worked out, because it wouldn't have been found that way from these type of problems. It's important. It's real. It's real. Of course, other things can go wrong that you remember vividly and you don't know what to do about. I was trying to give a lecture about chemical bonding. All involves positive charges and negative charges. I took some balloons. I rubbed one with cat's fur, and I rubbed one with lucite, etc. Whatever I did that day, all balloons repelled each other. Didn't matter what I rubbed them with, they just repelled each other. Okay? So that led to a small lecture on the expanding universe, and was that really due to excess charge or not? but you do remember this, and it's important in that aspect to let some things fail. We can't give a full lab experience as full research experience as part of a lab, but we can give a taste. And you can really get that with some labs, and I know at Stanford we're really trying to do that. I do, commend to you the possibilities of using more labs and lecture demonstrations. I think you got to keep this and use it if you want people to continue to go on in the sciences. It makes all the difference with your own hands and your own mind to think about something. Thank you. Sure, we go for grades, and my own experience is if you'll spend time with people in the lab, you will very easily be able to determine those you think are gaining from the experience and those who aren't. So I don't find it difficult to make some evaluation that way, but I don't know how to tell you more about that. In the course right now that I'm giving, and that Rebecca Whelan's the head teaching assistant, Chem 134, it's primarily a lab course, and we really allow not only something about what results are achieved, but a real important component is what the TAs think of the performance of the students, how well prepared they are in many ways. Do they understand the lab before they come in, and how it's written up? And we find writing up the lab report an important part of it in the process, not just doing the lab. Yes, some people have more manual dexterity than others. That's not what it's all about. It's partially what it's about, not all. You're lucky if you haven't experienced it, so you don't know what I'm talking about. It is a lab like a cookbook that has for you a recipe or a set of instructions which tells you exactly each step what to do, what to expect, and what follows after that. There's no thinking necessary much in this at all, and you get a well-controlled outcome. I certainly am in favor of student-teachers interactions. Don't want you to think otherwise. But there's a way to make problems where you have choices as to what to do that you need to think out as a person. What should I do? Should it matter? Should I run this in hot water or cold water, and why? And not be told, now you must run this only in cold water with no further explanation. To be instead be said, you now need to wash this, but you should decide whether you want to wash in hot water or cold water. I'll give you an example of what I'm trying to say, to make a difference between something which is very prescribed to something that causes you to wonder and say, well, which one's better for what I'm doing? And real life doesn't have a cookbook when you go to do something new. So you want to have some of that put in. Now, you can't have too much, because then you don't get closure. You have only a certain period of time. And you do want these labs in general to succeed. They have something that happens that you feel good about. I saw this happen. But so it's a balance. Okay? Yes? Oh, for example, today, almost no modern experiments are done without the aid of computers in either regulation or taking data or both. To give you an example, I'm not against computers. I'm against the concept that computers alone will replace labs. I want to integrate computers in labs, and we do. That's fine. There's very much a thought, though, that you can simulate reality with computers. And that by simulating this reality, see, we just don't need to do labs. We'll just do them with computers because it'll be cheaper. And, you know, computers don't smell like the chemistry department does, et cetera. You know, you get a sense of what I'm trying to say. And they cost a lot less after you've made the initial investment in them. And there's various arguments of this sort. And I'm saying there's still a reason you want to do things in the lab or have demos, I feel. Maybe, you know, this may change in time as computers get better, but right now I don't see it. I'm going to take someone of, yes? I have thought about a number of different experiments. I'm not so interested generally in doing historic repeats. At the time, I'll tell you why. Generally, anything that's discovered, this was sort of at the edge at that time of what could be done. And today we know how much better, how much easier and better to do certain things. That's valuable. That part's valuable. And to make things that involve the thinking and the reasoning aspect, that's valuable. So that I'm for. And indeed, we have at one of our labs that goes back to how people worked out what the atomic weights were and by making gravimetric precipitations of various chlorides containing compounds, etc. And we see how hard that was and what that was like. Yes. But again, my own experience is that it's not tied up with the grade. I mean, I know this is a very common feeling about grades, but what got me personally so excited to go on in chemistry is I spent a summer doing some X-ray crystallography, and it worked. I could understand it and do something. Okay, from playing with the crystals, seeing them grown, to getting real structures from them. And no one gave me a grade, and yes, they gave me a paycheck, and it was ridiculous. Forget that. That's not the point. It was this realization of that I could actually do it and understand it, and that it was fun. That's what I carried away. And I think the lab experience, I'm not so worried about what grade comes from it as I am what people take away from it about knowing about the world and themselves. I think they'll easily get this sense, particularly when there are others and there's comments being given. Have you thought of this? As long as there's interaction that goes along with just the lab. Initially, many of those labs were labs that it was very prescribed and clear what to do in the lab. There were no questions to be particularly answered. I'm not saying all labs were bad, but I'm trying to give you a sense of what was wrong. And so it's a challenge for us who make labs. And labs, again, I'll remind you, they're costly, they're time-consuming, and they're often left by the senior faculty as to someone else. Please, don't bother me with that. That's not, you know, I know that that's an infinite sink in terms of energy to get something to work. Okay? But yet it matters a lot. And can be done in a way, I think, that isn't a huge sacrifice. Have to think hard, though, which way. And I've tried to show you some examples. Yes? I don't mind if that's the conclusion that's reached, personally. I don't believe that everyone should pursue science. I don't. But I think they should given an opportunity, though, to experience that type of thrill of discovery. Some people will find it exciting more than others in that way. I'm not. And people often ask me, what is a thesis like? It's about graduate school. What's a thesis like? And I sort of tell them, well, it's a giant homework problem. There's a big lab component, see? And instead of, instead of having a week, you have sort of, well, several years. Many. And it's sort of open-ended, too. One of the important things to do, of course, is to know when to declare victory and go home with regard to a thesis, because learning just goes on.
Well, thank you very much.
Thank you.